matrix multiplication as the combination of linear transformation. If you have a vector space U and a vector space V, and you have a linear transformation T from U to V, that will take every vector x in U, transform it into a vector in V that we denote as T of x. And then here comes another transformation S that will transform vectors in V into vectors in W. And so, of course, S is going to transform this vector T of x into something that we denote as S of T of x. Because we can go from U to V and then go from V to W, it is the same as we can go from U to W via the transformation, that is the composition of S and T. Now the notation is a little bit awkward because on the picture, T is on the left, S is on the right. However, in the notation, S is on the left and T is on the right. But this notation makes more sense when you consider the algebraic expression of the transformation. So you start with x, you get T of x, and then you are going to get S of T of x. And you can see if you write algebraically, the S should be on the left of the T. And that is why people usually write S of T for the picture like this, right? Now let's be reminded that if you consider U to be some finite dimensional vector space, say Rp, and V to be a finite dimensional vector space Rn, and W to be Rm, then from the previous section, every linear transformation from Rp to Rn will be represented by a matrix A, right? So A will take x into A of x. Or in other words, you multiply the matrix A with the column vector x. And then S will be represented by a matrix B. Remember, after you multiply a matrix A and the column vector x, you are going to end up having a column vector in Rn, and then the B will come and multiply with that column vector, and you are going to get another column vector in Rm. To make it look similar to your textbook, I'm going to kind of switch the notation a little bit. Instead of A first, B later, I'm going to write B first, A later. Right. So that in the end, you will have A on the left of B. That's just for notation consistency with the book that you use. Here, I would like to be clear of the size of the matrices. If you go from Rp to Rn, then the size of the matrix B is n by P. And if you go from Rn to Rm, then the size of the matrix A is m by n. Now back to the composition S of T. The first observation we have is actually also a homework assignment that I asked you to do, 3.59. If S and T are linear transformation, then their composition is also a linear transformation. So the composition preserves the linearity properties. So back here, this is going to be another linear transformation that goes directly from U to W. So there should be a matrix C that represents the S of T. And finding what S of T of x is the same as multiply the C to the column vector x, right? And because they should be the same, then we have A of B of x equals C of x for all x in Rp. And because this is true for all x, we then can say, well, Cx just like A multiplied with B of x. And we define C as the product of A and B. And that's how we define the product of the two matrices. So each matrix will represent a linear transformation. When we compose these linear transformation, we are going to get another linear transformation. And because the new linear transformation has a matrix representation as well, that matrix representation is defined to be the product of the two matrices A and B. The third observation is not easy to see, but if you multiply two matrices A and B, it's the same as you multiply the matrix A with each column vector of B, right? A matrix B will have several columns. Each of the column is a column vector. So multiply a matrix with a matrix is the same as multiply the matrix with each of the columns of the later matrix. Why should this be true? It's not obvious to see. We are going to discuss it later, right? But first, let's consider an example of how we compute the product of the two matrices here. Here you have the matrix A multiplied with the matrix B given here. Let's perform the multiplication using the observation number 3 here. This is A and this is B. This one is the first column of B. We call it B column 1. And this is B column 2. So we are going to multiply A with the first column of B. In order to multiply A with the first column of B, we are going to multiply each of the row of A. So remember, when we define matrix vector multiplication, multiply a matrix with a column, we multiply each row of the matrix with the column to get the entries on the result column, right? Right, so we are going to multiply first row with this column. In order to multiply the row with the column, we multiply entries by entries and add the result. So 1 times 1 plus negative 1 times 3 plus 0 times 5. And then the second entry will be computed by multiplying row 2, the second row, with the column. So 2 times 1 plus 1 times 3 plus 3 times 5, right? Now 0 with 1, 1 with 3, 1 with 5. And then 4 with 1, negative 2 with 3, and 2 with 5. Right, and then you do the computation and you are going to get negative 2, 20, 8, and 8. Similarly, you will have to do that for the second column of B as well. So we are going to multiply A with the second column of B. And if we do the computation correctly, the first row of A multiplied with the column will give you negative 2. The second row of A multiplied with the column will give you 26. Next will be 10 and 12. And you are going to get the product of A times B. So the first column will be the result multiplying A with the first column of B. And the second column will be the result multiplying A with the second column of B. That's how you multiply matrix with matrix using the observation number 3. All right, so now I'm going to prove why should 3 be true. You want to know what is the representation for A times B, the product of A and B. Remember, this is a linear transformation. If you want to know exactly what it is, you have to consider the effect that it made on every single vector x. This is the same as C times x. But C is actually S of T of x. Now, what is S of T of x? You compute T of x first and then consider S on that one. So then how can you compute T of x? You multiply the matrix B with x. You are going to get the result, which is going to be a column here. And then you will compute S of that column. How can you compute S of a column? You multiply A with that column. But then, by the definition of matrix vector multiplication, you multiply a matrix B with a column vector x. It's the same as you consider the linear combinations of the columns of B, where the scalars are the entries of the column vector. And now let's look back to the diagram that we draw at the beginning. your X is in RP, so it should have P entries here. So you have P entries, so XP. And then the last column will be the column P. Now remember, the whole sum results in a column because each of the term is going to be a column vector. All right, and we know that matrix vector multiplication have the distributive law. So you can distribute A, and then you can use the scalar law to pull out the scalar x1 and xp here. When you multiply A with a column vector, the result is going to be another column vector. Here, the result is also another column vector. And then you combine these columns in a linear combination whose entries are x1, x2 up to xp. So it's the same as you are multiplying the matrix that is formed by each of the column here with a column vector whose entries are x1, x2 up to xp. And so the result product matrix should be in this form for all x in Rp. And that means that whatever we have here is the right representation for A times B. Because that is true for all x, so then you can plug x to be the standard basis. And you find that each column of A times B is the same as each column here. There's another way to compute the matrix multiplication faster. That is observation number 4. All right. You can compute directly entry-wise. For example, if you want to find the entry on the ith row and the jth column of the product matrix, then you just consider the dot product of the corresponding row of the former matrix with the corresponding column of the later matrix. For example, first of all, you will need to know how many entries we are going to compute. Look at the size of the matrix here. So the first matrix has 4 rows, 3 columns. The later matrix has 3 rows, 2 columns. In order for us to be able to multiply 2 matrices together, the number of the columns of the first matrix will have to be the same as the number of rows of the second matrix. Why? If they were different, then you will have the number of entries here not the same as the number of entries here. So you are not going to be able to multiply row and column. The result matrix will have the size where the number of rows is the number of rows of the former matrix. And the number of columns will be the number of the column of the later matrix. So that means the result matrix will have 4 rows and 2 columns. In other words, it is going to be of size 4 by 2. Now we are going to compute the first entry here on row 1, column 1. In order to find the entry on the row 1 and the column 1, we are going to multiply row 1 of the former matrix and column 1 of the later matrix. All right, so be ready to fill in the blank here. All right, so when you multiply row by column that way, you multiply 1 and 1, negative 1 and 3, 0 and 5. And you can easily get negative 2. If you want to compute this guy, then you first identify where it is on the product matrix. It is on row 2 and column 2. So then you turn your attention to row 2 of the first matrix and column 2 of the later matrix. That is going to give you the answer here. So 2 times 2, 1 times 4, 3 times 6. And so that is going to give you 26. Suppose you want to compute one more, this guy. Usually we do row by row or column by column. We are not going to jump randomly like this, right? This is on row 1, column 2. In order to compute it, you will have to consider row 1 of the former matrix and column 2 of the later matrix. All right, when you multiply them, do first with first, second with second, last with last. So you are going to get 1 times 2, negative 1 times 4, 0 times 6. And so that is going to give you negative 2. Right? You can repeat the process. You're going to get the whole result matrix here. So let me go ahead and fill out every single entries here, right? You just repeat the process for all 8 entries here, and the result should be the same as what you got previously. So let's take a look at how we are going to prove the observation 4 here. All right, so from observation 3, we already know that the product matrix will be consisting of the columns that are computed by multiplying A with the first column of B. And then you do that until you get the last column. Now, if you want to consider the entry on row I, column J of AB, first you will have to shift your attention to the column J of A times B. What does it look like? Now, the column J of the product matrix is somewhere in the middle here, right? And the J column will be computed by multiplying the matrix A with the column vector B, column J. Remember, although we write it this way, but it is in fact a column vector. This is a column. How are we going to compute this column? Remember, if you write it carefully, then you are going to have a matrix A with the first row last row. And then you multiply with the column J of B. The result, of course, is going to be a column vector. The first entry will be the result of multiplying the first row of A and the column here. So now you want to look at the entry on the ith row, right? So you have to look at here, the ith row. How are you going to compute this entry? Well, you are going to multiply the ith row of A with the column here. Well, that means that this obviously equals to row I of A multiplied with the column J of B, right? All right, so for the purpose of quick multiplication, you use observation 4. When you want to do proof, number 3 is in fact more effective in writing proof. All right, so here comes some properties of matrix multiplication. The first 3 properties can be checked entry-wise. This one, you write down A explicitly, and then you multiply with A, so this is n by n. If you can perform the multiplication, it has to be the n by n identity matrix. Now, if you perform the multiplication, you will see that, for example, you multiply row 1 and column 1. All entries starting from the second one will be multiplied with 0, and so they will contribute nothing in the result. Only A11 will be multiplied with 1, and that is going to give you the first entry on the first row and the first column being A11. You can do first row, second column, and you will see that right here is going to be 0, right? Above the 1 here is going to be 0. So A11 will be multiplied with 0, and all other A's will be multiplied with 0 below the second one, except A12. So the second entry on the first row, second entry, A12. Well, you can do that until the last one, and you will see, well, they actually produce A. All right, so this can be checked just by direct multiplication. So I'm not going to prove them, right? Just give you the idea of what is going on. Okay. So theorem 3.2 says that when you multiply A and B, initially we say that this is the same as multiply A with each column of B. The fact is that you can do otherwise. You can multiply each row of A with the whole matrix B and arrange them as rows. You are going to get the same answer as you multiply A with columns of B. Now, when you do the transposition of a product, it turns out that transposition of a product equals to the product of two transposition. But look, the order of A and B has been switched. And like in real number set, for matrices, you have associative property, you have left distribution, you have right distribution, you have scalar law, where you can bring the scalar out and multiply the matrices first. There is only one thing that you don't have, and I want to emphasize it. This will help you avoid every single common mistake when we deal with the matrix multiplication. That is, in general, we don't have the commutative property. There are cases in which the results are the same, but just special cases, right? All right, and in the homework assignments, I assigned you several exercises where we have some properties in the set of real numbers, and we thought that those properties is going to be carried to the set of matrices, but turns out that, be careful, many of them won't carry over because we don't have commutative property anymore. The last property that can be useful for you when you do the homework assignment, the rank of the product matrix will be less than the minimum of the rank of the two matrices here. All right, so first example, let T being the reflection over the y-axis and S being the reflection over the x-axis. Of course, that means T is going to be the linear transformation from R2 to R2, the same to S. Find the matrix representation for S of T, a reflection over the line y equals ax, whose polar coordinate equation is theta equals a fixed angle phi. This one has the matrix representation as the matrix cosine of 2 phi, sine of 2 phi, and then sine of 2 phi, negative cosine of 2 phi. T is the reflection over the y-axis. The y-axis in polar coordinate has the equation theta equals pi over 2 because that's the vertical one. So it forms an angle of 90 degrees with the horizontal axis. And the angle for x-axis is theta equals 0 radian. So this means that T is represented by the following matrix. Or in other words, T of x is going to be equals to the matrix that represented multiply with the x. So the angle is pi over 2, so you plug in pi over 2 here. You are going to have cosine of 2 pi over 2. And then sine of 2 times pi over 2. And you have sine of 2 times pi over 2. Negative cosine of 2 times pi over 2. And so it's the same as multiplying the following matrix with the x. And this is true for all x in R2. Similarly, you can find the S of x. Now we are looking for S of t, right? So S of t is another linear transformation, which is the combination of S and t in that order. If you apply it on X, then it is going to be S. So t is going to come first and take effect on the vector X because it's closest to X. And then S will come later and apply on the result. But then what is T of X? T of X is the same as multiplying the matrix negative 1, 0, 0, 1 with the vector X. The result is, of course, a column matrix with 2 entries, right? Now, whatever it is, the S will come later and apply on that. But apply the S on a vector is the same as multiplying this matrix with that vector. So this is the vector here. This is going to replace the vector X here, right? This one will replace this. And S is the same as multiplying this matrix. So it's going to be the same as multiplying 1, 0, 0, negative 1 with this guy. Now, although X is a column vector, but remember column vector is the special matrix. So you actually are multiplying 3 matrices together. And when multiplied matrices together, we have the associative law, which means you can group any of them as long as you keep the order. And instead of multiplying the last 2 first, I'm going to multiply the first 2 first, because I want to find a matrix representation for S of t, so I would want it to be like a matrix times X. All right, so what's left is just multiplying the 2. All right, the resulting matrix will be, and so this is the matrix representation for S of t. We really want to see what S of t looks exactly like, right? So if you write X as the column vector that has 2 entries, X1 and X2, then S of t, this transformation on the X is going to be S of t on X1 and X2 here. So this is going to be the same as you multiply negative 1, 0, and 0, negative 1 with this column vector X1, X2. And the result, negative X1, negative X2. How does this look like geometrically? So if you have the XY plane, that represents R2. Then you have a point whose coordinate is X1, X2. Then you are going to apply S of t, and that is going to give you the vector negative X1, negative X2. So this is S of t on X, and the black one was the X vector. All right. Well, you see that it's like you are rotating the point about the origin with the angle being 180 degrees. Right. So let's consider another example. Right, this example is to demonstrate that S of t and t of S are not the same. That means that matrix multiplication is not commutative. Part A, find the image of the unit squared under S of t and t of S to see that they are different. This is the unit squared. If you apply t first, this black square is going to get mapped into the blue one because t is the rotation of 90 degrees. So that is going to take this point 90 degrees, so to this point to this point, and this point to this point. The origin always stays as is, right? Linear transformation will map 0 vector into 0 vector. Now by the S transformation, the S is the reflection over the x-axis, so that is going to flip the square. So it's gonna make this line segment become this line segment. Whatever on the x-axis will stay as is, and the result is S of t of the unit squared. Now let's see what we are gonna have if we switch the order. We start with the unit squared again. Then T of S means you apply S first. S is the reflection across the x-axis, so it will turn the black unit squared into the red one here. And then here comes the T. So the T is the rotation 90 degrees. So it is going to take this point 90 degrees, so to this point. It will take this point 90 degrees to this point. And it will take this point 90 degrees to this point. Of course, the linear transformation always transfer the origin to the origin. So 0 becomes 0. All right. So T is going to take the red back to here. And so the result is going to be T of S on the unit squared. And so you see that S of T and T of S, they are completely different. Part B, the matrix representation for T is the rotation of 90 degrees. So that's going to be cosine pi over 2, sin pi over 2, negative sin pi over 2, cosine pi over 2. And so this is going to be the same as, all right, the matrix representation for S has been computed in the previous example, and you know that this is going to be, so S of T is represented by, so the matrix for S multiply with the matrix for T in that order, S of T, so S first, T later. And T of S is represented by T first and S come later. And if you perform the matrix multiplication, you see that they are different. So if you think of this one like A and B, then this is like B and A. So you can see that A times B is not the same as B times A, which means matrix multiplication is not commutative.